Hey everyone, so today we're taking a look at section 1.3, which is about measuring segments. So our goal today is to be able to compare and find the lengths of segments. So here we've got a little bit of a warm-up problem that deals with measurement. So it says, on a freshwater fishing trip, you catch the fish below. By law, you must release any fish between 15 and 19 inches long. You need to measure your fish, but the front of the ruler of the boat is worn away. Can you keep your fish? Explain how you found your answer. So the issue is that we don't have a front of a ruler here. It is worn away. So normally I could line up the tip of the fish with the 0, and wherever its tail is would be how long it is. So how could I take this fish and measure it using just what's left of the ruler? So what I would do is the first number I'm seeing right now is 17. So if I put the nose of the fish here at 17, I could figure out where the tail is. So let's see, this would be approximately like 29. So let's say it's from 17 to 29. Well, from here, I can find out how long it is. You could just count, or I know that 29 minus 17 is 12. So I could say that this fish is 12 inches long. Now, according to the problem, anything between 15 and 19 inches need to be thrown back. But this is 12 inches, so it is a keeper. Postulate 1.5, the ruler postulate. So the ruler postulate says that every point on a line can be paired with a real number. This makes a one-to-one correspondence between points on a line and real numbers. The real numbers correspond to points which are called coordinates. So this is essentially talking about what a ruler is. So a ruler is a straight line, and we've got a bunch of points. So usually at a quarter inch, a half inch, an eighth inch, every inch, or centimeters, millimeters, depending on which system you're using. And then we start putting some real numbers there. And so the idea is that we can have a one-to-one correspondence. There's only one 1-inch mark. There's only one 2-inch mark. There's a one 3-inch mark. And they're all equally spaced out. So this postulate is talking about the creation of a ruler. And again, it's one of those things that's so obvious, of course we can do that, and that is why it's a postulate. Postulate is saying this is acceptable. So a little more terminology here. We've got distance, and the distance is defined as the absolute value of the difference of the coordinates of 2 points. So the length of AB is the absolute value of A minus B. The way I always calculate it, I always take the bigger number and subtract the smaller number so I don't have to deal with negatives. But an absolute value just makes a negative and turns it positive, so it's going to work out either way. So again, a coordinate is a real number that corresponds to a point. That was from the ruler postulate. And they give us an example here. They're asking, what is the length of ST? So S is here at -4, T is over here at +8. They're asking, how long is that segment? So if I want to follow the distance equation exactly, I would say that ST is the absolute value of -4 minus 8, which is the absolute value of -12, which is 12. That's one way to do it. The other way to do it is that ST, the bigger number, is 8 minus -4, which also equals 12. And if you wanted to really go like caveman style on this, you could count it. Just know that you're going in increments of 2, so it would be 2, 4, 6, 8, 10, 12. So any way we do it, we're getting 12. I don't suggest going with the counting method, but more power to you if that's what you choose to do. On this slide, we're going to be talking about the segment addition postulate. And it's going to seem very straightforward, but let me tell you, come chapter 3, when we're going to use this a lot, I guarantee that like half of people at least will forget the segment addition postulate even exists, and we're going to have to review it. But the segment addition postulate is really nice. It says that if you've got 3 points, A, B, and C, and they're all collinear, and that B is between A and C, then segment AB plus BC is equal to AC. So if we look at this picture, we've got A, B, and C, they're all on the same line. And B is in the middle. If we go from A to B, and then A to C, and we add those two distances together, then we end up with the whole length of AC. So you can add two small segments together to get a big segment. That should make a lot of sense, which is again why it's a postulate. Example 1. All right, so this is our first example that we're going to probably have to do a calculation for. They tell me that EG, so EG is the whole length here. This is 59. And they want me to find the length of EF and FG. So EF is this part of the segment here. And then FG is this part right here. So according to the segment addition postulate, EF plus FG should equal all of EG. So this is FG, and this should be equal to all of EG. Now they do give us values for all three of these segments, just some of them have variables. So we're just going to plug in. EF is 8x minus 4. FG is 4x plus 1. And EG is 59. So thinking back to our algebra, we need to combine our like terms. So I've got 8x and 4x, so that's a total of 12x. And then I have, oh, this is a minus 14, not a minus 4. So we've got minus 14 plus 1, so that's negative 13 equals 59. So again, I'm trying to get my x by itself first, so I'm going to add 13 to both sides. And that gives me that 12x equals, let's see here, 72. So if 12x is 72, I need to get just 1x. So I'm going to divide both sides by 12. And when I do that, I get that x equals 6. Now, here's a mistake that I see all the time as a teacher. This is absolutely right. X equals 6, perfect. The mistake I see is a lot of people will get x equals 6 and move on to the next question. And that's not what we want to do, because we didn't answer the question. They asked what are EF and FG. They don't care what x is. We just needed to know that in order to find EF and FG. So I'm going to take this and I'm going to plug in. I know that EF is 8x minus 14. So wherever I see an x, I'm going to replace it with 6. So it's 8 times 6 minus 14. Well, that means that EF is going to be 8 times 6 is 48 minus 14. So EF must be 34. I'm going to do the same thing for FG. FG is going to be 4 times 6 plus 1. So this is 24 plus 1. So FG is 25. Now, something that's kind of nice about these problems, if I know that EF is 34 and FG is 25, let's add those together and make sure I do get 59, which 34 plus 25 is 59. So that's a very good indication that I did this problem correctly. It'll be very rare that you get two numbers that do add up to the whole length, but we made a mistake. So this is a very good sign that you did it right. If they don't add up, it means that you should go back and check your work. All right, so same type of problem here. They tell us that the whole length is 120, and then they want us to find the length of JK and KL. Well, I know that JK plus KL should equal all of JL. So that's segment addition postulate again. So they give us some values for JK and KL, so I'm going to plug those in. So I get 4x plus 6 plus 7x plus 15 equals 120. So let's combine our terms. 4x plus 7x is 11x. 6 plus 15 is 21, and that equals 120. So I'm going to subtract 21 from both sides. Gives me that 11x equals 99. Divide by 11. And I'm going to get that x equals 9. So to find JK and KL, I just need to plug in 9 for wherever I see x. So for JK, we're going to get 4 times 9 plus 6, which is 36 plus 6, which is going to give us 42. So to find KL, same thing here. KL is going to be 7 times 9 plus 15. So KL is going to be 63 plus 15. So KL is 78. Now, is this the right answer? Let's check. 42 plus 78 does in fact give us 120. So that is a very good indication that we got this problem correct. Congruent segments. So congruent segments are segments that have the same length. So the confusion that I get for students about this is if congruent segments are just segments that have the same length, why don't we just call them equal? And that's a very good question. So congruency talks about objects, where equality talks about numbers. So for example, I know we're talking about segments right now, but you could in theory have, let's say, congruent desks. So those are desks that are identical. They've got the same shape, the same size, the same weight. Everything about them is the same, but they're not numbers. They're desks. So congruency compares objects to each other, where equality compares amounts to each other. But we're going to use them almost interchangeably. You're going to see that probably for the next couple chapters. If I want to talk about two segments that are congruent, so let me draw like AB and CD. So again, these don't even have to be going in the same direction. I could say that AB, so AB with a bar, is congruent to CD with a bar. So I'm saying that these two segments are congruent. What does that mean? It means that their lengths are equal. So AB being congruent to CD means that the length of AB equals the length of CD. So if I told you that AB is 4, then CD must also be 4. Hopefully that's a little bit of clarity. This is the congruent symbol. It's like equals with a squiggle. Equals with a squiggle. And also in a picture, if you want to mark segments congruent, they put these little like tally marks. So these red tally marks for AB and CD let a viewer know that these are supposed to be congruent segments. And you can have as many segments as you want congruent. So I could draw 5 more segments, put a tally mark, and that means that they're all congruent. Example 3. So in example 3, they're asking, are AC and BD congruent? So really we're asking, are they the same length? So AC is here to here. So C is at 5. And then BD, B is at 3, and D is at 10. So they're asking, are these congruent segments? Do they have the same length? Well, from A to C, the bigger number is 5 minus -2. That gives me positive 7. Where BD, bigger number is 10, minus 3 is also 7. So do they have the same length? Yes, they do, meaning they are congruent. So I can say that AC is congruent to BD. Midpoint and segment bisectors. So midpoint and bisectors, they have a lot in common. That's why they're on the same slide. So a midpoint is a point that divides a segment into 2 congruent segments. So if you think about the word midpoint, it's like middle point. It's the point that's in the middle, so it's dividing a segment in half. So technically it's saying it's dividing into 2 congruent segments, but you can think of it as it divides it in half. Segment bisector, if you think about the word bisect, bi means 2 and sector is like sections. It's 2 sections. So it's a point, a line, a ray, or other segment that intersects a segment at its midpoint. So I always think of a segment bisector as something that cuts a segment in half. And we're going to find other types of bisectors. In the next section, we're going to have segment bisectors, and that cuts an angle in half. So midpoint is the point in the middle of a segment. It cuts it in half. And a segment bisector is something that cuts a segment in half. So for example, in this picture, L is a bisector because it goes through point B, which is a midpoint. Example 4. It says that Q is the midpoint of PR. So Q is the midpoint. That means that PQ is congruent to QR. And then they're asking, what are PQ, QR, and PR? Well, unlike the last example, we don't have any numbers. We don't know any of the segments. But I do know that PQ equals PR. So that means that 6x minus 7 is equal to 5x plus 1. The segments were congruent, therefore their lengths are equal, and that's how I set up my problem. So get all the x's to one side, I'm going to subtract 5x. I get that x minus 7 equals 1. Add 7 to both sides, we're going to get that x equals 8. So again, we don't want to make the rookie mistake of just calling it a day here. We need to take our 8 and plug in for x. So for PQ, it's going to be 6 times 8 minus 7. 6 times 8 is 48 minus 7, so we're going to get 41. Now, if we are right about this, that means that QR should also be 41, but I always recommend checking. So QR is going to be 5 times 8 plus 1, which is 40 plus 1. So QR is 41. I knew they were equal because I set them equal to each other. I said it was a midpoint. So to find PR, the whole thing, PR, well, that should be 41 plus 41, so we're going to get 82. And again, we kind of have a self-check here. PQ equals QR, and therefore, if we just add them together, we should get the whole segment, which is PR. So 41, 41, and 82. Example 5 is the same type of problem here. It says that U is the midpoint of TV, and they want to know what are the segments TU, UV, and TV. Well, if we have a midpoint, it means that we've got two congruent segments. Segments that are congruent are equal to each other. So I can say that 8x plus 11 equals 2x minus 1. So to solve for x, I need to get all my x's on the same side. I usually get things on the left. So let's subtract 12x from both sides. 8x minus 12x is going to give us negative 4x. Plus 11 equals negative 1. So I need to then subtract 11 from both sides. So if I do that, I'm going to get negative 4x equals negative 12. To get x by itself, I'm going to divide by negative 4. I get that x equals positive 3. So from here, I just need to plug in and then just double check my answer. So TU is going to be 8 times 3 plus 11, 24 plus 11. So that gives us a length of 35. TU equals 35. So let's check UV. UV is going to be 12 times 3 minus 1. That's 36 minus 1, which is 35. So UV is 35. That is the answer I would expect, which means the whole length of TV is 70. Okay, so lesson check. So for the lesson check, they say name each of the following. So for number 1, it's a point that's on DA that is 2 units away from point D. So AD is this green line here. And if I want to be 2 units away from D, if you go to the right, you're going to get F. If you go to the left, you're going to get B. But we want to be on DA, so it must be point B. For number 2, they're asking about 2 points that are 3 units away from D. So start with D, go 1, 2, 3, we get G. 1, 2, 3, we get A. So points A and G. And then for number 3, they're asking what are the coordinates of the midpoint of AG? So AG is over here. Where is the midpoint? It's going to be in the middle, which is point D, and has a coordinate of 0. And then last but not least, number 4, it asks what segment is congruent to AC? So I'm going to clean up my picture just because it's getting kind of messy. But being congruent to AC, there are many, many, many segments that will do that. So AC is here and has a length of 2. So I just need any other segment that has a length of 2. So maybe something like EG. So I can say that EG is congruent to AC because they have the same length. And that will do it for the lesson check. So some closing thoughts. I hope this section went well. I know we haven't had to do calculations in a little while, so this was our first time having to actually calculate things. The good news is that if this section made sense, the next section should make a lot of sense because it's almost identical but with angles. So instead of angle bisectors, instead of segment bisectors, we have angle bisectors. Instead of segment addition postulate, we have angle addition postulate. Same stuff, just different medium. So until next time, the homework should get posted soon. And if you've got questions, feel free to email me.